Hello and welcome to my science tutorials. In today's video, we want to talk about the WAEC chemistry past questions and answers for the SSSCE 1994 question number 1A and question number 1B. Alright, so let's have a look at the question. So SSSCE at 1994, question number 1A and question number 1B goes as follows. So A, we have to give the names, the relative masses and charges of the fundamental particles that make up an atom. So I take that again. So we have to give the names, the relative masses and charges of the fundamental particles that make up an atom. That is for the A. Now the B aspect is demanding that the element Q has two naturally occurring isotopes, that is Q3517 and Q3717, with relative abundance of 75.5% and 24.5% respectively. I. We have to define what isotopes are. II. What do the superscript and then the subscript in the symbol of the isotopes Q represent? And III, we have to calculate A, the relative atomic mass of the element Q, and then B, the molecules of Q2 that are present in 17.75 grams of Q2, given that the Avogadro's number is 6.02 times 10 raised to the power 23 particles per mole. Alright, so let's have a look at the solution for this problem. So let's look at the solution for the first problem, which is A. Okay, so for A, this is the solution for that problem. So the names of the particles. So the fundamental particles that make up an atom include the proton, the electron, and then the neutron. So these are the three subatomic particles or fundamental particles that make up the atom. Now for a proton, it has a relative mass of 1 and then it has a charge of +1. For an electron, it has a relative mass of 0 or 1 on 18,040, and then it has a charge of -1. Now for a neutron has a relative mass of 1, but it has no charge, it is neutral. Now for question number 1B, I, what are isotopes? So for isotopes, this is the definition for isotopes. Isotopes are atoms of the same element with the same atomic number but different mass number due to the difference in neutron numbers. So we are saying that isotopes are atoms. They are just atoms like any other atoms. They are atoms of the same element. They have the same atomic number but different mass number. The difference in their mass number is due to the difference in their neutron numbers, and that is what makes them isotopes. So they are of the same element. So for a typical example is the isotope for carbon. So let me give us an example. The isotopes that we have for carbon. So we have carbon 12. Okay, carbon has the atomic number of 7. So we have carbon 12. We also have carbon 13, which we normally use for dating the age of old substances. So you hear the terms like carbon 13 dating. And we also have carbon 14. So carbon 14. Okay, so this, we can see that we have just carbon, okay, with the atomic number 7 for all of them. So carbon. It has the same atomic number, but it is having different mass numbers. Okay, now the difference in these mass numbers is as a result of the difference in neutron numbers. Okay, so if we subtract this 7 over here, the atomic number, from the mass number, we'll get the neutron number. Okay, that is the amount of neutrons that is present in this particular carbon 12. The same thing for carbon 13, and then the same thing for carbon 14. So like I said, isotopes are atoms of the same element with the same atomic number but different mass numbers due to the differences in their neutron numbers. Alright, so the II aspect is saying that what do the superscript, the subscript and the superscript in the symbol of the isotope Q represent? So let's look at that. So if we look at Q, we have Q, capital Q here. we have a number here. Let me represent that with let me say A and then B. Okay, so where A is the superscript because it's at the top, and B is the subscript. Now the superscript, which is at the top, okay, represents the mass number. So it represents something we call the mass number. Now the subscript, which is at the bottom of the element Q, is what we are calling the atomic number. So basically put, for the element Q that has a superscript and then a subscript, the superscript is the mass number, and then the subscript is the atomic number. The subscript is the letter at the bottom over here. For this example, carbon 12, this is the atomic number, and then the one at the top over here is the mass number. So this is the subscript, this is the superscript, you can see over here. All right, so let's proceed to calculate the relative atomic mass for Q given these details. All right, so for Q, if we go back to our question, we have two elements of Q. We have the first one, Q, with mass number of 35, atomic number 17, and it has an abundance. Its relative abundance, the first one, is 75.5%. This is the relative abundance. Now for the second element, or the isotope, Q37, has the relative abundance of 24.5%. Now we are to calculate the relative atomic mass for Q. All right. Okay. So the relative atomic mass, let me use A and M to represent atomic mass, is equal to the summation of the mass number multiplied by the relative abundance all on total abundance. Okay, so this is the formula that we use to calculate the relative atomic mass when we are given questions like this. All right, so it means that the relative atomic mass for Q is equal to the mass number of the first element is 35 over here, so we have 35 multiplied by the relative abundance for the isotope 35 is 75.5, so we multiply that with it, 75.5, then plus, that is the reason why we have the summation here, then into bracket we have the mass number here is 37 multiplied by the abundance, which is 24.5, all over the total abundance is 75.5, which is the percentage over here, this one, the first one plus the second one. So we have 75.5 plus 24.5. So the relative atomic mass for Q is equal to 35 multiplied by 75.5 is going to give me 2,642.5 plus 37 multiplied by 24.5 is going to give me 906.5, all on 75.5 plus 24.5 will give me 100. Now note that the total abundance is always equal to 100. Okay, so from here we have, if we add the top, the numerator that we have over here, we are going to get 3,549 on 100, and this is equal to 35.49. So it means the relative atomic mass for the element Q is 35.49. Alright, let's proceed to look at the last aspect of that question. So the last aspect is saying that we are to find the molecules of Q2 that are present in 17.75 grams of Q2. All right, so when they said we should find the molecules of Q2, okay, that means we have to find the number of Q2. That is what we are to find. Now, for us to find the number of something, or the number of molecules, the number of atoms, or anything, we use the formula N is equal to small n multiplied by L, where the capital N is equal to the number of molecules or atoms, number of substance. Okay, the small n is the mole, and then the L is the Avogadro's constant. Now, it is clear from here that for us to calculate the number of Q2, the molecules of Q2, which is capital N, we need the mole, and we already have Avogadro's number. So the first thing we need to find is the mole. Now, mole is equal to mass over molar mass. In the question we're given the mass. So we're given, it said in 17.75, so we have 17.75 grams. Okay, now we need to calculate the molar mass of Q2, which is the capital M. The capital M, the molar mass of Q2, is equal to 2 multiplied by the relative atomic mass of Q, and that is equal to 2 multiplied by the relative atomic mass for Q is what we found over here, which is 35.49. So we have here 35.49. So this is going to give me 2 multiplied by 35.49 will give me 70.98 gram per mole as the molar mass of Q2. Now, the molar mass of Q2 is 2 multiplied by Q, because here is Q2. If it is just Q, it will just be Q here. If it is Q3, it will be 3 multiplied by Q. So we use the number, okay, the subscript over here to multiply the bigger number when we are calculating the molar mass. Okay, so from here our mole is equal to, our mass is 17.75 divided by our molar mass is 70.98. So our mole is equal to 17.75 divided by 17.98 will give us 0.25 mole. Okay, so now that we have the mole, and then we know Avogadro's constant because we're given in the question, we can proceed to find the number of molecules of Q2. So number of molecules for Q2, which is N, is equal to small n multiplied by capital L. Small n, which is our mole, is 0.25 multiplied by our L, which is the Avogadro's number, is 6.02 times 10 raised to the power 23. This is equal to 0.25 multiplied by 6.02 times 10 raised to the power 23 will give me 1.51 times 10 raised to the power 23 molecules. 23 molecules. Okay, so it means that the number of molecules of Q2 that is present in 17.75 grams of Q2 is equal to 1.51 times 10 raised to the power 23 molecules. So thank you so much for watching. This is how we solve problems on mole concept as well as the subatomic particles in chemistry. So thank you once again for watching, and I will see you in the next video. Bye bye.